This is slide number 63 and I am your presenter Asloob Mudassar. Imaging of sharp boundaries. You see that this is in continuation of the previous four methods that we have presented in order to determine which of the two systems, that is coherent system or incoherent system, which of the two systems is better. You see that in that connection we have presented the spectral contents of intensity images of both coherent and incoherent system. We have also presented the two-point resolution criterion for both coherent and incoherent systems. The third one is that we have presented the imaging of sharp edge. The fourth one is that we have presented the speckle imaging because that is more concerned with coherent systems. So after presenting those four, we are now presenting the imaging of sharp boundaries. Another effect which is noticeable in the images of sharp boundaries or sharp edges under coherent and incoherent illumination makes the two types of images appear differently. A ringing effect is observed at the edges in a coherent image, whereas a blur effect, that is a smooth variation in intensity, is noticeable in incoherent image of an object. A sharp edge in the two-dimensional space is shown in the figure. So let me explain this diagram. Let's first read the caption. The images of a sharp edge under coherent and incoherent illumination. So you see that on the leftmost we have the sharp edge, a completely dark region and a completely transparent region. So the between the two is a sharp edge, you see. And then we have the image of this sharp image under coherent imaging system, which is shown in the middle. You can see that there are ringing effects. Ringing effects can be seen at the place of the edge, and then you know that finally we ultimately end with the highly transparent region. And in the third case we have an incoherent image of sharp edge. You see that we have a dark region, and on the right hand side we have the transparent region, and in between them we have a region which we say that it is a smoothness variation in intensity. So this region which is gray is actually a smooth variation in intensity going from a black to white region. So you see that the prominent thing in the case of coherent imaging is the ringing effect at the position of the edge. Look at this ringing effect. This is particularly associated with the coherent imaging system of edges, of sharp edges. The mathematical equation of a coherent image of a sharp edge can be written following equation number 138 in the following form. So ICC stands for the coherent intensity as a function of U and V is equal to the absolute square of kappa convolved with the amplitude image. So kappa is a function of U and V. That is, you know that kappa is a point spread function, and we say that it is an image of a point source. And convolution is with the UG. UG is the amplitude, is the geometric optics amplitude image as a function of U and V. So you see that there is a convolution, and in the second step we have replaced UG with an edge function. So EDGE edge function is a function of U minus U naught comma V, which means that the edge occurs at the position U is equal to U naught, as given in equation number 149. This is, you know, that a two-dimensional version because it involves two coordinates U and V. We would like to write the one-dimensional version so that we can make the mathematical computation or mathematical analysis simple. A one-dimensional analog of this equation takes the following form: IC of U is equal to absolute square of a kappa convolved with edge function. So you see that here we have omitted the V variables. So we have only U variable present, and you know that in the edge we have U minus U naught, which means that the edge, that is the center of the edge, or the edge occurs at the position U is equal to U naught, as given in equation number 150. The edge U minus U naught function can be defined in the following way. So let's define the edge function. Edge of, here we are going to define the edge function using coordinates at the object plane, because zeta and eta are the coordinates at the object plane, And you know that at the object plane the edge will be defined as edge of zeta minus zeta naught is equal to 1 for zeta minus zeta naught is greater than equal to 0 and 0 otherwise, as given in equation number 151. Which means that with respect to this sharp image of the edge, it means that zeta naught exists at the center of the edge. So zeta is equal to zeta naught is at the center of the edge. On the left hand side we have the opaque region, and on the right hand side we have the region which is clearly transparent, and this region is represented by 1. So for all values of zeta greater than zeta naught which is located at the edge, the clear aperture is reproduced as given according to this equation number 151. Following equation number 144, that is this equation which was presented in equation number 62. So following equation number 144, kappa of u is defined in the following way. Kappa of u is equal to a multiplied by j1 of 2 pi over lambda zi w into u divided by w into u. This is equation number 152. The mathematical equation of incoherent image of a sharp edge can be written following equation number 39 in the following form. So you see that here we have presented for the coherent system the image of the edge using coherent system. Here we are going to present the image of an edge using incoherent system. On the left hand side we have an intensity image. The subscript in stands for the incoherent image, for incoherent intensity as the function of image coordinates u and v. And you know that on the right hand side we have kappa mod square convolved with ug mod square, because by definition of the intensity image it is given according to the right hand side of equation number 153. And you know that kappa mod square is an intensity image, is an intensity point spread function convolved with here we have replaced ug in the second step by the edge function. So convolved with the absolute square of the edge function at u minus u naught comma v. So again we are going to write the one dimensional version of equation number 153 in equation number 154. Only using the coordinate u. So I in as a function of u is equal to kappa is equal to absolute square of kappa of u convolved with the absolute square of edge of u minus u naught. And here you know that we have omitted the variable v. So according to this diagram, that is the sharp edge, the coherent image of the sharp edge, and the incoherent of the image of the sharp edge. If you take the cross section of these all the three functions, all the three images, the cross section is plotted over here in this figure. So let me read the caption. Line cross sections through the center of sharp edge. Its coherent and incoherent images are shown in the figure. So here we have on the vertical side we have plotted IU over U naught, which is the normalized intensity. The maximum value of that is equal to 1. And on the horizontal axis we have plotted U. And you will see that the edge occurs at U is equal to 0. So here the sharp edge occurs at U is equal to 0. So the sharp edge according to this one, that is the image on the left, the sharp image for sharp edge is represented by this solid edge which is sitting at u is equal to 0, and it goes straight up to value of 1, and then it becomes horizontal because it attains constant value equal to 1 according to the clear aperture in the above figure. So this is the sharp edge, we have also labeled that one. And now we are going to talk about the coherent image. You know that in the coherent image it starts before the edge, that is it starts from the region which corresponds to the black region. So you see that it corresponds to the black region, that is the ringing effect starts just before the just before the location of the edge, that is starts from the dark region. So you see that this for the coherent image it starts from the dark region, that is from this one, goes straight up, cutting the edge at 1/4 of that value, and then 1/4 of that value, and then goes straight and even crossing the maximum value which is 1, goes even above the value of 1, and then you know that it goes up and down, that is according to the ringing effect. It cycles and asymptotically at the end it approaches to the value of 1. And then let's talk about the incoherent image. Incoherent image, in the incoherent image, the diffusion also starts from the gray scale, that is we have shown the gray value, for example in this case, also starts in the dark region. That is the blurred effect or the smoothness variation in intensity starts from the black region. It is slowly increases and it cuts the sharp image at an intensity of half, that is at a value of 0.5, and then it goes smoothly above, and then you know that it remains below 1 and slowly it increases and asymptotically it approaches to the value of 1. So this is the difference between, you know, that the sharp edge we have shown. We have also shown the coherent image onto the sharp image, and we have also shown the incoherent image over to the sharp image. So the three images are shown together so that we can make the comparison very easily. A ringing effect is obvious from the coherent images, whereas the blurring or the edge smoothing effect is obvious in the incoherent images. In coherent image, the value of the signal just before the edge position rises above the brightest intensity, which is 1 in the actual edge image, and then approaches this value asymptotically through cyclic variations about this value, which means that the value, that is the ringing effect, will increase the value of the maximum value, which is 1, will increase beyond 1, and then it becomes lower and then again lower than 1, and then again higher to 1. And you know that this variation is cyclic, and asymptotically this variation reduces asymptotically and then approaches to the value of 1. In the incoherent image, the value of the signal just after the edge stays below the actual value and approaches this value asymptotically in a smooth way. The actual edge position in a coherent image can be located at 1/4 of the asymptotic value. So you see that if you want to locate the actual value of the edge from this presentation, from these plots, you will say that 1/4 of the value will exist, that is this value where it cuts the edge at a value of 0.25, that is 1/4 of the value of the edge. Then you know that here this locates the position of the edge, and for the incoherent system the value has to be 0.5. When for the incoherent system the value rises to the half value for the in the normalized case, then you see that we would say that it is the location of the edge. The actual in the incoherent image, the value of the signal after the edge stays below the actual value and approaches this value asymptotically in a smooth way. The actual edge position in a coherent image can be located at 1/4 of the asymptotic value, whereas this position occurs at 1/2 the asymptotic value for an incoherent image. These values are indicated in the plots given in the figure above. From the one-dimensional plots, it is evident that the incoherent image of the edge is more closely related to the actual edge and gives superior results in comparison with the coherent image of the edge. So you see that here in this example we have shown the superiority of the incoherent image over the coherent image. So this completes an image. This completes an example number 5 that we have presented, so that we can compare the coherent and incoherent systems in different scenarios and in different domains and establish the superiority of some of the techniques. That which one, that either the coherent system is superior or the incoherent system is superior. So that up to this point we have not derived any ultimate solution or ultimate decision for our ultimate conclusion that could say anything in favor of any of these techniques. So the discussion must be continued. Now the speckle effect. There is another effect called speckle effect which occurs in coherent images and is associated with the spatial coherence of the illuminating sources. So for the speckle effect to appear, the sources that illuminates the object or illuminates any surface area must be spatially coherent. It has no analog for the incoherent images obtained with visible light. To observe the speckle effect, an object transparency is illuminated with a coherent light and is viewed through a ground glass, or equivalently an object transparency is multiplied with a phase screen which randomizes the phase of the illuminating beam at the object plane. The coherent image thus formed as a result of the interference contains speckle. You know that the formation of the coherent image is due to the interference effect. And you know that the image would then contain speckles. For coherent images with speckles, the equation 149 can be written in the following form. You know that speckles are actually the grain, the grainy pattern in an image, because points, very small points of graininess structure will appear, shining them above the intensity, above the mean intensity, and at sometimes they are below the mean intensity. So you see that we can write the coherent intensity for an image obtained with under phase screen, that is in the presence of the phase screen, that is in the presence of the speckles. So the speckle coherent intensity is given by equation number 155. Here we have amplitude PSF, AMP stand for amplitude PSF, convolved with amplitude object multiplied by the phase screen. So the object is actually an amplitude object multiplied by the phase screen, and these two multiplication of these two will be okay. So our actual object is amplitude object multiplied by the phase screen. These together will convolve with the amplitude PSF, and the absolute square of this whole quantity will give you the speckle image, which we call I coherent, as given in equation number 155. For incoherent imaging, the above equation, that is equation number 155, will take the following form. So I incoherent is equal to absolute square of the PSF amplitude, that is the amplitude PSF mod square, convolved with the absolute square of the amplitude object multiplied by the phase screen. So the convolution between these two absolute square quantities will give you an incoherent image as given in equation number 156. So here the point spread PSF amplitude is actually the kappa of u comma v. So kappa is actually the amplitude image which we have been discussing many times, in our slides. So PSF amplitude, or the kappa of u and v, was defined in equation number 143. It is the amplitude PSF, or the impulse or amplitude impulse response of the coherent imaging system. Object amplitude. What is the object amplitude? Object amplitude is the amplitude object which gives the amplitude transmittance through an object transparency. And phase screen contains random phases. Phase screen can be realized practically by placing a ground glass plate in contact with the input object transparency. So you see that what we do in equation number 155, that we have an object, amplitude object, in the form of a transparency, and then we can multiply it by the phase screen with that object, which has a random variation in its thickness, so that it can produce a random variation in phase. These two are multiplied together, forming actually one piece of object, and then that is convolved with the amplitude point spread function, and then the absolute square of that one at the image plane will give you the I coherent. And similarly for the incoherent case, but you know that in the incoherent the imaging equation are different as given in equation number 156. So you can compare equation number 155 and 156 to see the difference. For simulation of equation number 155, the phase screen can be generated in the following way. Phase screen is equal to e to the power iota times the random phase generator in the range from 0 to pi by 2, as given in equation number 157. It generates the real numbers randomly in the range from 0 to pi by 2. So the random number generator gives you the numbers in the range from 0 to pi by 2, and you know that iota is being multiplied in equation number 157, and the exponent of this whole quantity will give you the phase screen variation. So the thickness in the phase screen will be governed by this equation. the size of the phase screen. And you know that here when we are multiplying the two things, that is the amplitude object and the phase screen, the size of both these two objects must be identical, so that we can combine the two together. The size of the phase screen should be the same as that of the amplitude object. The thickness of the phase screen can be controlled by the range in which the random numbers are generated. So if you change this region of the random numbers, here we are using from 0 to pi by 2, but if you make the range increased from 0 to, for example, say pi or 2 pi, then you know that the thickness of the phase screen can be controlled by the range in which the random numbers are generated. For incoherent imaging, the presence of the phase screen remains ineffective, as clear from the following equation. So look at the equation number 158. Here we have considered only a part of the object part which we have shown in equation number 156 in an incoherent image. So let's evaluate the amplitude part, that is the absolute square of object amplitude multiplied by the phase screen. Here we are going to evaluate in equation number 158. So on the right hand side we have separated the two quantities, that is the absolute square of object amplitude multiplied by the absolute square of phase screen. And you know that if you take the absolute square of the phase screen on both sides, and as in equation number 157, you will get 1 on the right hand side. So the phase screen from equation number 158 will be omitted, and we have only absolute square of object amplitude. So if we put back it in equation number 156, you will notice that the phase screen does not appear in the formation of the incoherent image, which means that the spectral effect cannot be noticed in an incoherent image. Now simulation results of the incoherent imaging in equation number 156 is shown. Phase screen did not affect the output image. Output image is slightly a blur version of the input image due to finite size of the intensity point spread function. So the data used was, in the simulation we used the data lambda is equal to 632.8 into 10 to the power minus 6 millimeter, that is the red wavelength from the helium neon laser, and Zi is equal to 1200 millimeter, which is the image distance, and A is equal to 1, which is the amplitude of the illuminating beam. Here you can look at, let's read the caption first. Incoherent image on the right. For example, this one is the incoherent image on the right mode side, right sides of the and the original object on the left side, with an incoherent intensity, with an incoherent system. That we have obtained these incoherent image on the right side, and this is with intensity point spread function shown in the middle. So intensity point spread function is shown in the middle. So the original object will convolve with the intensity point spread function and will produce an image which is on the right hand side, and this is called an incoherent image. And you see that there are no spectral effect on the image in the right hand side, that is in the incoherent image, because we have explained earlier that this phase screen, formation of the phase screen or inclusion of the phase screen in our imaging system would not affect, and you know that we shall get only an incoherent image as if the phase screen is not present. Simulation results of the coherent imaging equation 155 are shown on the next slide. That is, these results correspond to the equation number 155, because there we have included the phase screen, and you know that here the phase screen will do matter, and the coherent image is produced as we have shown over here. So you see that over here we have shown 3 point spread functions. Point spread function 1, which is the same point spread function as we have used for the incoherent imaging system. So the point spread function 1 in the coherent image is the same as the point spread function 1 shown in figure in an intensity image, in an intensity point spread function. But you know that the difference is that this is an amplitude point spread function, and the point spread function we have shown over here is an intensity point spread function, that is the absolute square of the point spread function shown for the coherent system, which is amplitude PSF1. And you know that if we use amplitude PSF1 in the equation, in this equation, for example over here in the equation number 155, the PSF point, the amplitude PSF we have shown here which is shown on the leftmost side, which we call as amplitude PSF1, then you know that the image that we obtained is on the top of that one, which is the speckle image 1. And you know that here W, the size of the object that we are using, is 32. And you know that the same is the size that we used with this object. So the original object was of the size W is equal to 32 in the incoherent case, and for the first coherent case we have used the same value of W. But you know that if you reduce the value of W, that is the size of the aperture, that is the size of the limiting aperture, the size of the amplitude PSF will look like as shown in amplitude PSF2 diagram. Here we have used W is equal to 16, and you know that the corresponding speckle image 2 is shown above. You will see that the speckle size has increased in this image. And in the third case, where we have used amplitude PSF3 with W is equal to 8, thus the aperture size is reduced further. So the speckle, so the pattern of the airy disk will increase, and of course the size of the speckles as shown in the picture above will also increase, as shown in speckle image 3. The speckle images, the speckle size, the size of the speckle is much greater than in the previous two cases. So let's read the caption. Coherent images of the original object from the previous slide, that is we have used this object as the original object. So this original object was convolved one by one with amplitude PSF1, then amplitude PSF2, then with amplitude PSF2, and then the absolute square was taken, and then the images are shown above. So coherent images of the original object from the previous slide with exit pupil side of radius W when viewed through a ground glass phase screen with randomly coded phases between 0 and 0.5 pi, that is pi by 2 in the upper row, and the corresponding amplitude PSFs in the bottom row. So using different W values, W is equal to 32, W is equal to 16, W is equal to 8. In these images, we have produced amplitude PSF1, amplitude PSF2, amplitude PSF3, and then you know that these amplitude PSFs were convolved with the original object shown on the left in this diagram, and then after convolution, we have taken the absolute square of this quantity, as in equation number 155, and the corresponding images are shown in the above row as speckle image 1, speckle image 2, and speckle image 3. So now let's read some statements. Simulation results of coherent imaging equation number 155 are shown on the next slide, which I have partially explained. The incoherent image from the previous slide can be compared with the coherent image 1, speckle image 1, as both used the same pupil size, that is W is equal to 32. When the pupil size is the same, it means that both systems used the same PSF, amplitude PSF in case of coherent image, and intensity PSF in case of incoherent image. The mean speckle size, the mean size of the speckle goes inversely with the pupil size, as obvious from speckle image 2 and speckle image 3. That is, when W will increase, when W will decrease, the speckle size will increase inversely. So this is shown in the upper row. The mean speckle size in a coherent image is roughly equal to half the width of the main lobe. So notice this is very important point. The mean speckle size in a coherent image is roughly equal to half the width of the main lobe in the corresponding airy pattern, amplitude PSF. There are cases, for example holography, in which coherent imaging is mandatory and speckle effect cannot be avoided by any means. Speckles thus deteriorate the quality of coherent images in comparison with incoherent imaging. In this particular case, incoherent imaging is thus superior. In this topic, we have discussed in this topic and the topic in the previous slides, including the topics from both these slides, we have discussed the comparison between the two imaging systems in terms of number 1, spectral contents of coherent and incoherent intensity images. The second one is that 2-point resolution under coherent and incoherent imaging. The third one is edge effect, imaging of edge, with coherent and incoherent illumination. The fourth one, finally, the speckle effect associated with coherent imaging in visible light. The overall conclusion should go in favor of incoherent imaging systems, especially with the narrow band illumination, and in general with broadband illumination, but in the presence of appropriate time averaging. Speckle effect mainly hinders the performance of coherent images. Techniques have been developed to reduce speckle effect either during experimentation or through image processing techniques after the images are recorded, but these techniques are not much effective and the image resolution are compromised. Bandwidth extension in coherent and incoherent images. Coherent and incoherent images are always limited in bandwidth. The size of the exit pupil actually controls the bandwidth of an imaging system. An imaging system with a higher bandwidth allows higher spatial frequency contents of the input object to reach at the image plane. If we compare the intensity images obtained from the coherent and incoherent imaging systems with identical system parameters, we say that the bandwidth is more or less the same in both cases, as obvious from figure slide number 62, through which different modulation transfer functions are shown. Coherent systems are linear in amplitudes, whereas incoherent systems are linear in intensities. It is more appropriate to talk about amplitude bandwidths when dealing with coherent systems and intensity bandwidths when dealing with incoherent systems. Amplitude images from coherent imaging systems are converted into intensity images by the physical detectors placed at the image plane to record the images. Amplitude images can be recorded using holographic based techniques in which a coherent reference beam is added at the recording plane and an interference pattern is recorded from which the amplitude image can be obtained. It follows that the amplitude bandwidth of a coherent imaging system is half that of the intensity bandwidth of an incoherent imaging system. The size of amplitude transfer function in case of coherent system and the size of the optical transfer function in case of incoherent system determine the bandwidth of respective imaging systems. These transfer functions are specified at a plane referred to as the Fourier or spectral plane. Transfer functions thus determine the classical resolution in respective imaging systems. The limit to classical resolution is due to diffraction at the exit pupil in an imaging system. The larger is the bandwidth, that is the size of the transfer function, the smaller is the point spread function. Size and higher is the resolution. Limit to bandwidth means limit to resolution. Extension of a bandwidth beyond the classical limit is regarded as super resolution. Super resolution can be achieved either through experimental arrangements or through extension of a bandwidth by using intensity or amplitude images. The latter approach may be regarded as a theoretical one. Next, we are presenting theoretical approaches for the extension of bandwidths, assuming absence of noises at any level and assuming diffraction limited system. Here we are considering only spatially bounded objects, either illuminated with coherent illumination or with incoherent illumination. Such objects have Fourier spectra, which can be described with two-dimensional analytical functions. It is well established fact that if an analytical function is known accurately in a small region of space, in this case Fourier space, the entire analytical function can be determined using analytical continuation. Thus, for spatially bounded objects, if a Fourier spectrum is known accurately in a small region of Fourier space, then the whole object spectrum can be determined accurately and uniquely. When dealing with coherent systems, amplitude spectrum or a small part of it is concerned, whereas intensity spectrum or a part of it is considered in case of incoherent imaging system. Consider a thin cosinusoidal amplitude grating bounded by a square aperture of width 2W and is illuminated with a narrow band incoherent source. The incoherent image of the grating is given by the following equation. So incoherent image of the grating is equal to the object amplitude, the mod square of the object amplitude, and here the object is the amplitude transmittance of the grating, the mod square of that one convolved with the intensity PSF or the amplitude PSF mod squared as given in equation number 159, where OBJ with the subscript AMP represents the amplitude transmittance of the object grating in this case and is given by. So we have written the object amplitude as a function of image coordinates u and v is equal to the square root, because half, you see that we have taken the half power to the curly brackets, which is the square root of grating function in the square bracket 1 plus m cos of 2 pi into 1 over L into u for all value of v, and multiplied by the two-dimensional rect functions or two one-dimensional rect functions. The one rect function is rect of u over 2w, the other one is rect of v over 2w. So this is the object that we have defined. So the object is bounded in a rectangular aperture of size 2w by 2w. So this is the grating is bounded in a square aperture of width 2w. The one-dimensional version of equation number 159 along with the equation 160 is. So here we are writing the one-dimensional version of the above equation, that is we are using only one variable u. So incoherent image as a function of u is equal to the absolute square of the object amplitude as a function of u only convolved with the amplitude square of the absolute square of the amplitude PSF as a function of u only. And you know that here we have written the grating function as a one-dimensional function, and of course the one-dimensional rect function which is u of 2w and convolved with the absolute square of u. And you know that absolute square of u, which is kappa is a function, kappa defined as a function of u, only one variable u, which is an amplitude PSF, and we have taken the absolute square of this one to convert it into intensity PSF as given in equation number 161. So equation 161 is actually a one-dimensional version of the equation 159 along 160. The spatial frequency of cosinusoidal function in the object is f naught is equal to 1 over L, as obvious from this grating function given in equation number 160. So 1 over L will give you the spatial frequency of the cosinusoidal fringes given by f naught is equal to 1 over capital L. The parameter m can take values in the range from 0 to 1, because m would determine the visibility of the grating function. For mathematical simplification and for explanation of bandwidth extension in the simplest form, we want to find the geometric optic image which can be obtained from equation number 161 by choosing the system PSF as a delta function. For mathematical simplification and for the explanation of bandwidth extension in the simplest form, we want to find the geometric image which can be obtained from the equation number 161 by choosing system point spread function as a delta function. So here, if we choose kappa mod square as a delta function, we shall get the following result as shown in equation number 162. And you know that this is the intensity geometric optics image as a function of u. Now let's find out the Fourier transform of equation number 161. So here we are going to determine the Fourier transform of equation number 161. So we have applied the Fourier operator on both sides. I am not going to explain these mathematical results because I have explained many times in the course on Fourier optics. So you should look at the previous slides if you are interested in the detail of this one. So I am just talking about the final result as given in equation number 163. So I have represented the Fourier transform of the incoherent intensity by capital G as a continuous variable fu. So fu is the frequency variable fu, and capital G is actually the spectrum of the incoherent image. And on the right hand side it is given by 2W sinc of 2W fu plus m times W into sinc of 2W, and within the parentheses we have fu plus f naught, and then the third sinc function plus m into W into sinc of 2W as a function of within parentheses fu minus f naught, and this whole parenthesis is multiplied by the k in, which is the incoherent transfer function as a function of fu, as in equation number 163. The Fourier transform of equation number 162 follows directly from equation number 163 and is given below. So here is one equation number 162. This is one equation number 162. So if you want to take the Fourier transform of this quantity, what you need to do is that you need to skip only the transfer function, that is the k in from equation number 163, and then you will get the Fourier transform as shown in equation number 164. So you see that for an incoherent image obtained that is the as the spectrum of the incoherent image, we have used capital G as the symbol, and for the geometric optics image we have used the symbol GG. So that is simply G, capital G, and here we are using GG because GG is the spectrum related with the geometric optics image. The subscript G stands for the word geometric. And fu, you know that if you relate fu with the space variables, fu, the frequency, the Fourier frequency fu is equal to u over lambda z, is a Fourier domain parameter. That is, fu is a Fourier domain parameter, and u over lambda z is its representation in space domain, that is in the image coordinates. Ig of u is the intensity image under geometric optics. Absolute square of PSF amplitude is the intensity PSF, and that is the PSF of an incoherent imaging system. When the geometric optics image is convolved with the intensity PSF, incoherent image I incoherent of as a function of u is obtained. The corresponding images are shown in the figure. So let me read the caption first. Plots of incoherent geometric optics image on the left hand side, incoherent intensity PSF in the middle, and the incoherent intensity image on the right hand side. So look at the geometric optics image Ig as a function of u, defined in the range from minus w to plus w, and you know that this is a grating function. This grating function is actually will convolve with the intensity point spread function shown in the center, and these two will convolve to give you the value of the incoherent image on the right hand side. So this incoherent image actually is defined according to this equation. For example, this one, incoherent image, and you know that the amplitude, the geometric optics image is defined from this equation, and the point spread function, you know that the square of the point spread function is kappa. We have already defined that the amplitude PSF is actually kappa, and you can see that this is the mod square of a kappa in one dimension, because all these rails are in one dimensional mode. So we have used one-dimensional equations, equations in order to represent this data. So this is the simulated data. You can see that we have obtained the incoherent intensity image by the convolution between the geometric optics image convolved with the intensity PSF. The cosinusoidal function Ig of u is limited by the rect function to a width of 2w, as you can see, from minus w to plus w. Gg is the spectrum of Ig. It has 3 peaks due to the 3 sinc functions. Functions given earlier. One is centered at fu is equal to 0, the other two are centered at fu is equal to plus minus f naught. So you see that we are actually plotting the spectrum of this one. So G, capital G, is the spectrum corresponding to the incoherent image, and you know that it has 3 sinc functions. It means 3 peaks corresponding to the sinc functions. So let me show you these in the diagram. So look at let me read the caption first. Geometric optics incoherent intensity image spectrum. Geometric optics incoherent intensity image spectrum GG on the left side. Intensity PSF spectrum, that is the transfer function of the incoherent system, in the center, and the incoherent intensity image spectrum that is the spectrum or the Fourier spectrum of the incoherent image represented by capital G on the right side. So you multiply these two, that is capital GG multiplied by Kn will give you capital G. And you know that in the GG you can see three peaks corresponding to three sinc functions. So GG is the spectrum of IG. It has three peaks due to the three sinc functions. One is centered at FU is equal to 0, the other two centered at FU is equal to plus minus F naught. K in, which is the intensity. K, what is K in? K in actually the incoherent transfer function. You can see its shape in the middle, and this is the OTF or the optical transfer function. If you take the mean value of K in, it becomes the OTF, optical transfer function. So it is the optical transfer function of the spectrum of the intensity PSF. The multiplication of GG with the K in gives it the spectrum of the incoherent image capital G, as you can see we have shown in this diagram. Beyond the cutoff frequency of plus minus F naught, you see that here we have shown the frequency, cutoff frequency for this spectrum, plus F naught, minus F naught to plus F naught. This is the cutoff frequency of the spectrum. So can we extend the spectrum beyond this cutoff frequency? Because only we shall absorb the spectrum within these range, that is from minus F naught to plus F naught. Beyond the cutoff frequency of plus minus F naught, no frequency information is passed, and within the pass band, the frequency contents are tapered off. The frequency contents are tapered off. You can see the tapering. The tapering is shown in the transfer function. So this tapering is multiplied with the GG, and you will also see there is a tapering, but you know that the tapering is not evident. So if you compare this capital G with the GG on the left hand side, you can see that the other two sinc functions have vanished out because of the transfer function which is being tapered on both sides, and the cutoff frequency for the transfer function is minus F naught to plus F naught. So the other two peaks, sinc peaks, are not visible in the final spectrum of the incoherent image on the right hand side of the spectrum. The problem of bandwidth extension lies in constructing the full spectrum capital GG as a function of FU from the measured band limited spectrum capital G of FU. So you see that this is over capital G is over measured spectrum, and you know that it is band limited, but the full spectrum is obtained from capital GG. So you can see that on the left we have the full spectrum because it corresponds to the geometric optics image, and you know that after passing through the incoherent imaging system we have the spectrum which is only limited in the pass band region given from minus F naught to plus F naught. Are there any means we can extend the spectrum of this one and obtain the spectrum of and obtain the spectrum corresponding to the geometric optics image? Is it possible? So if it is possible, it will be called extension of bandwidth. So the problem of bandwidth extension lies in constructing the full spectrum GG, that is this spectrum on the left, from the measured band limited spectrum capital G of FU, that is this on the right hand side. In real situation, the intensity image I incoherent is recorded and its Fourier spectrum capital G as a function of FU is computed. Bandwidth extension techniques are then used. Let me read the caption of this figure. Representation of incoherent imaging transfer function. Representation of incoherent imaging transfer function K in as a function of FU and the geometric optics incoherent image spectrum capital GG in a single display. Here we have shown the two quantities in the single display, that is the spectrum corresponding to the geometric optics image which is capital G small g, and multiplied with the K in, that is the incoherent, that is the optical transfer function or the incoherent transfer function of the incoherent imaging system, multiplied by these two shown together. A continuous image O as a function of xy can be retrieved from its sampled version O as a function of n prime capital X comma m prime capital Y by injecting two sinc functions. The sampling theorem is reproduced below. So you see that we can obtain a continuous image from the sampled image using the sampling theorem, which we have already discussed in the very beginning of this course. And the sampling theorem is this, which is reproduced in equation number 163. So on the left hand side you have O as a function of x comma y, and on the right hand you have the sampling theorem. And you know that under these two summation signs you have sampled object, which is O of n capital X comma m capital Y, and with the two we have injected two sinc functions there. One, and you know that in the argument of one sinc function we have capital Fu, and in the second function we have the argument capital Fv, and these two determine the width of the spectrum along the small x along the Fu direction, and Fv and capital Fv is actually the width of the spectrum along the small Fv direction. And small Fu are using small f, that is Fu and Fv. These are actually the Fourier axes on the Fourier domain, and capital F are give you actually the width of the spectrum along the Fu and Fv directions respectively. So you see that summing up all these informations, you can produce the original continuous object on the left hand side given as O of as a function of x comma y. And the one dimensional of this is reproduced in equation number 166. So in the one dimensional version we are retaining only one variable x and omitting the y variable. So O as a function of x is equal to summation from n is equal to minus infinity to plus infinity. So we have O of n multiplied by capital X, and the sinc Fu within parentheses we have x minus n into capital X also. And you know that we have replaced capital Fu with 1 over capital X on the right hand side in equation number 166. Because if you are setting a capital Fu, that is the width of the spectrum, is equal to 1 over capital X, where X is the sampling interval at the object plane, then it means that you are using critical sampling. In the critical sampling, the spectrum that are produced are just you know that separating from each other. So in the one dimensional case you have to sum up all over the n variables from minus infinity to plus infinity with the inclusion of sinc function, so that you can obtain a continuous image. So you have to sum up the whole data to get one value of the continuous variable Ox, where capital X is the sampling interval at the object plane and is related to the full width Fu of the spectrum along the Fu direction, small Fu direction, through the relationship that till capital X is less than or equal to 1 over Fu. So this is actually the relationship between the sampling at the object plane and the width of the spectrum in the Fu direction. Simply we can find a relationship between the sampled version of the object spectrum, that is capital GG, from its continuous version capital GG through the following relationship. Before I go further, I would like to say that there is one minor mistake. Please keep it in your mind that in the rest of the equations going from 167 to onward, the quantity on the left hand side which I have written as GG or as a function of Fu should be read as capital G without the small subscript g as a function of U, and only small subscript will appear in the summation sign on the right hand side. So please omit this small g on the left hand side, because this quantity is actually known. Capital G of Fu is known, and using these known quantities we have expressed these known quantities in terms of the quantities which are unknown and which we have to recover. So you see that these quantities on the left hand side are the continuous quantities, and on the right hand side we have Gg as a function of n times sigma. and you know that giving the values of n will makes capital G subscripted to small g within the sigma notation are the sampled values, whereas on the left hand side we have capital G as a function of fu are the continuous values. So please omit small g on all the rest of the equations on the left hand side. Omit small g and read it only as capital G as a function of fu. The reason is that we actually have capital G over here within this interval from minus f0 to f0 plus f0, and these are the measured values. And using these measured values, we want to recover the whole spectrum capital G with the subscript small g in the range of the whole spectrum. That is, we want to extend capital G to find capital G as a function of fu. So the capital G on the right hand side is all known, and the capital G with the subscript small g as a function of fu is what we have to find by extension of the bandwidth of the signal given on the right hand side. So on the left hand side I shall read only g or as a function of fu, and you know that we have expressed this one as a function of the summation of from minus infinity to plus infinity, and within that we have one dimensional function with capital Gj as the sampled spectrum with arguments n into sigma and multiplied by the sink of 1 of sigma, and within the parenthesis we have fu minus n times capital sigma, as in equation number 167, where sigma is the sampling interval at the Fourier plane and is related to the full width 2w of the object along the u direction through the relationship that is sigma is less than equal to 1 over 2w. Okay. So what is the problem now? The problem is that we want to find the quantity on the left hand side is known, that is capital G as a function of fu is known because we have measured this quantity, and on the right hand side we have capital G with the subscript of small g as with an argument of n times sigma. This is a sampled version of the spectrum, and this is unknown. We have to determine this is only known within the pass band. So you know that the quantity on the left hand side is known only within the pass band from minus f0 to plus f0, and the sampled quantity on the right hand side is also known within the pass band from minus f0 to plus f0. But you know that we have to find this quantity, that is capital G with a subscript of small g. We have to find this quantity outside the pass band as okay. So let's proceed further. In principle, the index n cannot take infinite values. The Fourier plane may be localized by using n to vary within limits, and the above equation may be written as given below. So we have capital G as a function of fu on the left hand side, and we have the quantities on the right hand side. And you know that the only difference between equation number 168 and 167 is that we have limited the value of n, small n, to the capital value from minus capital N to plus capital N, because we want to set some values. Infinity is nothing, you know. Choice of an appropriate n value can help to extend the spectrum beyond the classical diffraction limited cutoff frequency. So capital G of fu is based on the addition of 2n plus 1 sampled values of this. So this read this as capital G of fu only is based on the addition of 2n plus 1 sampled values of Gg. So Gg is the sampled values, you know, we are talking about, multiplied by the sink functions centered at each fu is equal to n times omega. So extension of this one into the polynomial. So this means, you know, that when we are using capital G, this capital G actually is only G only. So extension of capital G as a function of fu in the polynomial would contain 2n plus 1 unknowns, and thus would require 2n plus 1 equations similar to equation number 168. How many equations are these in equation 168? Actually, this is one equation. For one value of fu on the left hand side, you will have all values from minus n to plus n on the right hand side. So actually this is a summation. This is actually one equation containing containing 2n plus 1 terms. And you know that if you have another value of fu, then again another set of equations as given in equation number 168. So actually 168. So if you, for example, if you are using fu, for example fu on the left hand side, if it contains for example k values, then you know that 168 will also on the right hand side you have to have 168 values. So expansion of left hand side into a polynomial would contain 2n plus 1 unknowns and thus would require 2n plus 1 equations similar to equation 168. So you see that if you have 2n plus 1 unknowns, we need 2n plus 1 equations to solve the problem. Measurement of G within the pass band at a distinct set of 2n plus 1 values would help to generate 2n plus 1 simultaneous equations, and equation 168 may be reproduced replacing u with a running index k in the following form. So you see that now let's talk about equation number 168 in more detail. You know that the quantities on the left hand side are known. How many values are there? These are 2n plus 1 values given by k index. K goes from 1 to 2n plus 1 values. So actually this gk, this g only, g of fk will give you how many values? 2n plus 1 values. So let me explain in this figure with the help of this figure. So this g on the right hand side from minus f naught to plus f naught will give you known values. How many are they are numbers? They are 2n plus 1 numbers, and the index k giving you from 1 value to 2n plus 1 values. So these are all values which are known with the index k. And what we have to do is that we have to find g on the left hand side of this figure. We have to find the bandwidth extension using this limited bandwidth extension on the right hand side. Okay, so you see that for each value of k, capital G on the left hand side is known because it belongs to the passband region, which we have already measured as I have shown in the diagram. And on the right hand side you will plug in these values, and running the small index, small n goes from minus capital N to plus n. It means that on the right hand side how many terms you have? You are summing actually 2n plus 1 terms for each value of k. So you can separate out. So for each value of k, so keep on putting values of k. Then you know that what will you get? You will get actually 2n plus 1 equations corresponding to each value of k. You will get one equation, that is one row, and with 2n plus 1 n values you will get k rows, and each row has a values from minus n to plus n according to my small index n. So you see that you can write the right hand side into a matrix, giving a matrix corresponding to the single functions, and then the column vector giving the values of gg. And on the left hand side, which is capital G only, and these are the measure values, you can also write down a column vector for the left hand side. So the column vector for the left hand side is a known values, whereas the column in the middle, the matrix in the middle is the matrix corresponding to the single functions, and on the right side of the matrix you have another column vector giving the values which are the unknowns, values of the capital G with the subscript of small g. So you have one column on the left hand side which are the measured values. Then on the right hand side you have one matrix giving the one matrix of 2n plus 1 by 2n plus 1 values corresponding to the sync values, because the sync giving you the sync function giving you the whole matrix. And then you know that on the right hand side of that matrix you have one column giving the values of this gg, which are unknown values and the sampled values in equation number 169. So you see that here we want that this matrix should not be a singular matrix. For that one we require that Fk should not be equal to n times sigma, because if this is equal to this condition will occur, then you know that the matrix will be singular and the solution will not be possible. To keep the equations distinct, the above equation should observe the following restrictions, that is Fk is not equal to n times capital sigma. The solution of the above equation can better be realized in the matrix form. So capital G of Fk on the left hand side will be transformed to a column vector of 2n plus 1 known values, whereas capital Gg, which is the sampled version and with the argument of n into sigma, will be transformed into a column vector of 2n plus 1 unknown values. These two column vectors will be related through a matrix 2n plus 1 by 2n plus 1 matrix with 2n plus 1 n values and n other 2 plus 1 k values. So we have a matrix between these two column vectors, between these two columns. One column on the left hand side contains 2n plus 1 known values, and the other column on the right hand side contains sampled versions which are unknown values, and in between them we have the matrix 2n plus 1 by 2n plus 1 matrix. Now this capital G of Fk corresponding to left hand side quantity are the 2n plus 1 known values related to the passband from minus capital N to plus capital N, and this capital G as a function of n sigma, which is the sampled version, provide 2n plus 1 known values related to the passband from minus capital N to plus capital N, and also there are 2n plus 1 unknown values outside the passband. So the sampled versions contains known values 2n plus 1 in the numbers and also 2n plus 1 unknown values outside the passband. So the equation 169 can be written as, in the presence of because we are also combining capital K over here, so the small index n will run from minus capital N plus K to plus capital N plus K, and you know that K goes from minus capital N to plus N, and for each you know that n will run, and actually these will give you actually a matrix, you know. The sink will give you the matrix. So these two, that is capital G within the sigma notation Gg, and the sink function can be written in equation number 170 as one m matrix, as a matrix representing as a matrix denoted by capital M multiplied by the sigma unknown, and these sigma unknown are actually capital Gg values, with some of the values which are 2n plus 1 values corresponding to the passband are known, and beyond the passband we have 2n plus 1 values which are unknown. And you know that on the left hand side we have sigma measured. Sigma measured correspond to capital G of Fk, which are the known values within the passband of the signal. So this sigma unknown can be obtained by inverting the equation. So we can write this equation as given in equation number 171. So sigma unknown is equal to inverse of the matrix M multiplying to the sigma measured values. So let me read some text above. Measured sigma measure contains 2n plus 1 values in the column vector, whereas the sigma unknown contains 2n plus 1 values of Gg and sigma in the column vector. Capital M is a matrix of 2n plus 1 by 2n plus 1 elements which are based on the sinc function. The matrix can be inverted for sigma unknown provided the inverse of capital M, that is m minus 1, m raised to power minus 1 exists. The inverted matrix is given below as given in equation number 171. So M inverse would exist when none of the two equations given in equation number 169 are identical, or the matrix does not contain any row dependence on any other. Knowing sigma unknown using equation 171 means that 2n plus 1 values of capital J of the sampled versions of capital Jg outside the passband are known. When a large bandwidth extension is attempted, the noise level for the highest frequencies may become greater, making the matrix as ill-conditioned matrix where the solution is dominated by noise. We have described how critical sampling at the Fourier plane can be used to reconstruct the frequencies outside the pass band of the spectrum. The cost to pay is to measure the pass band spectrum at 2n+1 distinct frequencies. Okay, next we are going to define the iterative method of bandwidth extension. You know that this was the analytical method. That is, analytically you can do the extension of a bandwidth. Now here we are writing down, here we are describing the iterative method of bandwidth extension. That is a completely computational method. The method uses two prior data sets. Intensity image is positive, so this is a condition that we shall be applying in the algorithm. So all the negative values will be set in the intensity if they occur. So intensity image is positive. This is the one condition. Its spatial size is known. So the size of the image is also known, which we say that the spatial size is known. So if the spatial size of the object is known, it means that the spectral contents, that is the Fourier spectrum within the passband, are also known. So these are actually the two conditions, and the third condition, that is the spectral contents, will ultimately rise as a consequence of the second condition. An intensity image should always be positive, and this is referred to as the positivity condition. The initial intensity image being an output from an incoherent image, from an incoherent system, may not spatially bound, but we can consider it to be spatially bounded image on the basis that the object imaged by the incoherent imaging system was spatially bounded. So object is spatially bounded, and when it passes through the optical system, the image, if not initially spatially bounded, we shall consider it to be spatially bounded, or we shall only submit a part of that one which is spatially bounded to our iterative algorithm. The flow chart given in the figure shows the necessary steps involved in the working of the iterative algorithm, which are explained below. So let me first of all give you the description of the flow chart. Let's read the caption. Flow chart explaining important steps of an iterative algorithm for bandwidth extension. So what we shall do, we shall get the initial image, which is only available to us, the initial intensity image obtained from the incoherent system. The spectrum of this one will be referred to as the reference spectrum. So initial image is known, its spectrum, its Fourier spectrum is called reference spectrum, is also known. So you know that this initial image is fed as an initial image for the first time as a starting point. So now the algorithm will start. Look at the right arrow. This intensity image will go towards the right arrow, that is the application of a positivity will be applied. That is, if there are any negative values contained in the intensity image, those negative values will be rejected and will be replaced by the 0. And the spatial boundedness, that is, we shall truncate the object. If the object is larger in size, we shall truncate the object to the spatial boundedness of the object. For example, if the size of the object is known, then that will provide us the spatial boundedness, and we shall be truncating each time the intensity is exceeding this spatial size. We shall truncate to the spatial boundedness. And you know that after this condition, we shall take the Fourier transform, and then we shall obtain the spectrum of the image. This spectrum is then, you know, that will be subject to the condition, that is the application of spectral content replacement in the passband by the reference spectrum. So you see that this spectrum may be slightly greater than the size of the original spectrum. But you know that the part of the spectrum, the part of this spectrum which is equal to the reference spectrum over here. So the reference in the passband, the spectrum in the passband will be replaced by the spectrum from the reference spectrum. So this spectrum, the part of this spectrum which belongs to the which belongs to the pass band will be replaced by the reference spectrum, and then the whole spectrum will be inverse Fourier transform to get the intensity image. This intensity is fed second time, will be checked second time for the positivity and the spatial boundedness, and then the Fourier transform is taken for the second time. The spectrum is obtained for the second time. This is the central part of this spectrum, or you can say that the pass band of this spectrum will be replaced by the reference spectrum, and then you know that the whole total spectrum will be inverse Fourier transform for the second time to obtain the intensity image for the third time. And then of course these cycles will continue until the intensity image there are no variations are observed in the intensity image and also in the spectrum. So if there are no intensity variations are observed during these cycles, then you know that it means that we need to end up the algorithm because we have reached the final decision. So let me read some statements corresponding to this flow chart. An intensity image obtained from an incoherent imaging system is regarded as initial intensity image. An intensity image obtained from an incoherent imaging system is regarded as initial intensity image, and its Fourier spectrum obtained computationally is regarded as the reference spectrum, as you know that explained in the first step. Initial image from the imaging system and the reference spectrum obtained from this initial image. The initial intensity image is fed to a 4-step algorithm as the intensity image. In the second step of the algorithm, the intensity image is checked for positivity and spatial boundedness. The negative values in the intensity image are replaced by zeros if any. So in this, then the size of the image is checked. If the size of the image is larger than the initial intensity image, then the extra size is padded with zeros. This is referred to as the spatial bounding the image intensity. These two constraints are referred to as image constraints. In the third step, this image is Fourier transformed, and a retrieved spectrum would have some frequencies lying outside the passband. The width of the passband here is assumed to be the same as that of the reference spectrum. In the fourth step, the spectral contents lying within the passband are replaced by the reference spectrum, and the resulting spectrum is inverse Fourier transformed to obtain the intensity image as the new input for the second cycle of the algorithm. The cycles are repeated unless no change is observed in the intensity image and consequently in the spectrum of the image. The final spectrum thus obtained would have frequencies lying outside the passband, which may be regarded as the extrapolated frequencies. Presence of noise in the initial intensity image may be a limiting factor in the convergence of the algorithm. Incorrect spatial boundedness may lead to incorrect results or failure of the convergence. The two bandwidth extension techniques were presented just for introduction to the idea. A large number of techniques are now available, but the discussion on those is beyond the scope of this presentation. So this is the end of slide number 63.